We'll now look at a special type of linear system called a homogeneous system. And in order to do that, we start with what is a homogeneous equation? A homogeneous equation is anything of this form a1x1 plus a2x2 all the way up to anxn equal to 0. All of the a's are real numbers, the coefficients, and the x's are the variables. So a homogeneous system would be a linear system consisting of all homogeneous equations. So here's an example of a homogeneous system. We have 6x1 minus 7x2 plus 4x3 equal to 0, 6x2 plus 9x3 equal to 0, and 4x1 plus 3x2 plus x3 equal to 0. So we want to know about the solutions to homogeneous equations in systems. So homogeneous systems always have at least one solution. And this is known as the trivial solution, where all of the x's are just zeros. So the question becomes, does it have a non-trivial solution? Does it have more than one solution? So let's look at some examples. So here's my homogeneous system. And I want to solve it and see if it has a non-trivial solution. Well, the first step is to move it to an augmented matrix. Now that we have the augmented matrix, we need to turn the first row, first column into a 1. And we'll do this by multiplying the first row by 1/2. We know the second and third row won't change, so they'll stay the same. And we then just divide the entire first row by 2. That then gives us 1, -3, 2, 0. Our next goal will to get its zeros below this one. We already have 1 0, so we just need to turn this 1 that I have highlighted here into a 0. And we're going to do this by subtracting the 2 rows, negative row 1 plus row 2. We're only manipulating the second row, so the first and third rows won't change. We then have negative row 1 plus row 2. So negative 1 plus 1 is 0. Negative 3 is 3. Minus 2 is 1. Negative 2 minus 6 is negative 8. And then 0 minus 0 is 0. Now that the first column looks the way we want it to, we start on the second column. The second row, second column is already a 1. So instead, we need to get zeros both above and below that 1. For the top one, the negative 3, we'll need to do 3 row 2 plus row 1. The second row won't change here. We then have 3 times 0 is 0, plus 1 is 1. 3 times 1 is 3, minus 3 is 0. Negative 8 times 3 is negative 24, plus 2 is negative 22. And 3 times 0 is 0, plus 0 is 0. We then want the 0 below this 1. And for that, we're going to do negative row 2 plus row 3. So we have negative 0 plus 0 is 0. Negative 1 plus 1 is 0. Negative 8 is 8. Minus 8 is 0. And then 0 plus 0 is 0. So we now see that this does have a non-trivial solution. In fact, I can't get a pivot in this third column. So let's start writing out our equations. The first row gives me x1 minus 22x3 is equal to 0. And the second row gives me x2 minus 8x3 is equal to 0. We then want to solve for our basic variables, x1 and x2. So we have our solution where x1 is 22x3, x2 is 8x3, and x3 is any value. And we can see that if we let x3 be equal to 0, we get the trivial solution. Any value for x3 that we pick that is not 0 will give us a non-trivial solution. One of the other important things to notice about this is our augmented column never changed in our row reductions. The last column was always just 3 zeros. And no operation we could do will ever change this column in homogeneous systems. It will always just be a list of zeros. Therefore, when we deal with homogeneous systems, we often omit this column and don't include it, and instead just deal with the coefficient matrix. So let's do another example where we look at that. My next system is x1 plus 4x2 minus 2x3 equal to 0, 2x1 plus 9x2 minus 7x3 equal to 0, and negative 2x1 minus 3x2 plus 6x3 equal to 0. The first step is to put this into our augmented matrix, but remember we're going to ignore the augmented column this time and just deal with the coefficient matrix. So here's the coefficient matrix, and we can start our row reduction. We already have a 1 in the first row, first column, so we need to get zeros below it. Let's start with the second row. It's currently a 2, so we need to subtract 2. So we'll do negative 2 row 1 plus row 2. I know my first row isn't going to change. I then have negative 2 times 1 is negative 2, plus 2 is 0. Negative 2 times 4 is negative 8, plus 9 is 1. Negative 2 times negative 2 is 4, minus 7 is negative 3. And we can now move on to the third row. The third row is a negative 2, so we need to add 2. So I'll do 2 row 1 plus row 3. So 2 times 1 is 2, minus 2 is 0. 2 times 4 is 8, minus 3 is 5. 2 times negative 2 is negative 4, plus 6 is 2. So I now have the first column the way I want it. The second column already has a 1 in the second row, second column, so we need zeros both above and below this. Let's start with the one below. It's currently a 5, so I need to subtract 5. I'll do negative 5 row 2 plus row 3. I know the second row is going to stay the way it is right now. I then have negative 5 times 0 is 0, plus 0 is 0. Negative 5 times 1 is negative 5, plus 5 is 0. And then negative 5 times negative 3 is 15, plus 2 is 17. And while I haven't finished reducing my matrix, I am going to stop here, mainly because I already know I have a pivot in the first row, first column. I have a pivot in the second row and second column, and this 17 means I'm going to have a pivot in the third row, third column. So every column has a pivot. There are no free variables. So this particular system only has the trivial solution. You can continue the process and continue reducing it, and you'll get the same answer. However, if we notice that if we have a pivot in every single column, we're guaranteed to have only the trivial solution, we may be able to get out of a couple of steps in our row reduction.